All right, maybe we got a little ahead of ourselves. So let's kind of go back to basics here. Filter basics. This is the ARRL radio handbook. And there are filter types, right? So this is the basic filter type. So is it a low pass? It passes low frequencies and it blocks high frequencies. Is it a high pass? Is it a band pass? Or is it a band stop? Sometimes you'll hear band stop. Sometimes you'll hear notch filter. Usually when it's a notch filter, it's a narrower excursion, but you can use either term, band stop, notch filter. Filters can have different frequencies. They can have different cutoff frequencies, so you can shift these graphs back and forth, different frequencies. You can have different amounts of what's called roll-off, is how fast does it attenuate. And we'll take a look at that. You can also have different bandwidths. How wide is the band pass? The band, right? What defines the band? How wide is the band? How wide is the band? There are other things about ripple, and that is, it looks like it's very, very flat and then rolls off. These are ideal curves. A real one might have some wigglies in it. We'll take a look at that. All right. Not exactly sure what's the best order to do things in here. Let's talk about filter types first. Let's see here. A couple things. All right. So we talked about filter types being high pass, low pass, band pass, things like that. But there are also filter types that are the configurations, and different filters operate differently, and they're named, okay? This is a filter cookbook out of Stanford's EE 133. So upper division EE class, talking about filters. One of the first filters you'll learn about is the Butterworth, also known as maximally flat filter. So what does it mean to be maximally flat? So here's a Butterworth filter, and the band pass, where it actually passes things, is very, very flat. There's no wigglies in it. It's a nice, straight, smooth line. Very, very nice. Okay? So maximally flat filter, you would choose a Butterworth. There's another filter that's also maximally flat. We'll talk about a little later. And there's something called a Chebyshev filter. You may have heard that before. And it says here also known as equal ripple magnitude. So a Chebyshev filter is going to have wigglies, okay? It will have a steeper slope to the line. Let's see here, where is a Chebyshev? Yeah, here's a Chebyshev. So a Chebyshev can have, instead of a nice flat roll-off, it can have a little peak in it. That's a type of Chebyshev. Chebyshevs can also not give all the energy. They can actually attenuate in the passband as well. And they can also, let me get a different picture out. Chebyshevs, like I said, can be wiggly. So let's take a look at that, okay? So here's kind of a cartoon version of a Chebyshev. So it's wiggly but then it falls very, very fast, okay? So wiggly. All right. There's also a Bessel filter, which is also maximally flat, okay? It's not as good as a Butterworth as far as frequency response, but it's better as far as linear phase response. That's kind of an advanced topic. I'm not going to talk about phase in this particular, I don't think I will, but I don't think we'll get to phase information on filters. This transient response, and phase response. And I'm not going to be able to touch this, I don't think, in this short little video series. And then there are elliptical filters, also known as Cauer filters. And so if you take a look at all those together, all together now. Here's the Cauer filter. It's spelled C-A-U-E-R. So the elliptical filter will have wigglies and then other wigglies. So it's a wiggly filter as well. The Chebyshev filter has equal wiggles. The elliptical filter will have unequal wiggles. All right? And then if you put them all together, you kind of get this type of idea where the Butterworth filter we started out with is the green one, and it falls really, really nice. I told you that the Bessel filter is kind of the same thing, but not quite as good. It's nice and flat, but then it doesn't roll off as fast. And that's in order to keep the phase information better. The Chebyshev is the wiggle and falls very, very fast. And then the elliptical just wiggles everywhere, but it also has the sharpest cutoff. All right. So, which one do you use? Which one's best for you? Well, that's a lot of knowledge. That's a lot of what do you really need. But it really comes down to, do you need flat? Do you need sharp? Do you need phase? Do you need transient? And then you get to choose which one you want. All right, let's talk about filter order. You may hear that. In fact, yesterday, I kind of glossed over it when I was looking at orders in order to match the filter that we had. I just kind of typed it in knowing what it was, but we'll talk about how you can determine what order you need. The first thing about order is basically it's almost like a amplifier stages. If you had, an amplifier with a first stage and a second stage and a third stage, imagine a filter with a first stage, a second stage, and a third stage. And each stage makes it roll off faster. So here, this is a first order Butterworth. It comes in and it rolls off like this. Here's the second order. Here's the third order. Here's the fourth order. All right. So they have more components, more L's and C's, but they attenuate faster. There's a spec you can put on that is amplitude normalized to the frequency. So you can hear decibels per decade, things like that. It means that if here's the cutoff frequency the filter's designed to, and this is 10 times that frequency. And if you go 10 times that frequency, how many dB lower is the signal? With a first order filter, it's minus 20 dB. With a second order filter, it's minus 40 dB, then it's minus 60 dB, then it's minus 80 dB. And so that's one measurement of filters is how steep this thing is in dBs per decade. Okay. I should mention you'll also see dB per octave. Instead of dB per decade, dB per octave. What is an octave? An octave is just the power of 2. It's just double the frequency. So if this is 10 times that's a decade, 10, and here's 2, here's 1, here's 2, okay? So this line right here, draw it in a little darker, okay, this would be the decibels per octave. Okay, so it would be 6 dB per octave, yada, 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 right? So sometimes they specify filters in dB per octave. Sometimes they specify them in dB per decade, okay? I like dB per decade better. Here's a Chebyshev filter, and you can see the bandpass has some wiggles in it. Okay, so it's wiggly, wiggly, wiggly. Here's the design frequency for the cutoff. It has very, very sharp cutoff. This is a third order filter. This is a 6th order filter. And you can see that the wiggles are different. Between the 3rd order, it has fewer wiggles. The 6th order has more wiggles. All right, let's go back to the Stanford document here. What filter do I want? We talked about some of these already. What type do you want? High, low, bandpass. What's the center frequency? What's the bandwidth of the filter? What's the cutoff? What's the roll-off rate? How many dBs per decade? That kind of thing. Minimum attenuation required in the stop band. So how much do you really need to get rid of, right? So if you only need to get rid of 20 dB of the unwanted signals, or you need to get rid of 50 dB of the unwanted signals. What's your input impedance? Sometimes it's 50 ohms, sometimes it's 600 ohms, sometimes it's 6,000 ohms. What's your output impedance? What's your overshoot in the step response? We haven't talked about that yet, so we'll just ignore those last two there. But yeah, so here's some things you need to consider.